Assalamu alaikum, brothers and sisters. Welcome to the journey of Quest, where we quench your thirst of knowledge. Have you ever pondered about the tiny particles that make up everything around us? Just think about it. Every object you can see, every surface you can touch, even the air you breathe is composed of these minuscule entities called atoms. They are the smallest unit of matter, yet they hold within them a world of wonder and complexity. Atoms, you see, have a unique structure. At their core, they house protons and neutrons, while electrons whirl around this nucleus in a dizzying dance. This structure, simple yet intricate, is the foundation of everything in our universe. And then there's the periodic table, a chart of all the known elements, each defined by its atomic structure. It's like a cosmic map, guiding us through the vast universe of atoms. So, are you ready to dive in and explore this incredible world? By the end of this video, you will have a better understanding of the fascinating world of atoms and the periodic table. Let's start our journey at the heart of every atom, the nucleus. This tiny hub of activity is home to two types of subatomic particles, protons and neutrons. The protons carry a positive charge, while the neutrons, true to their name, remain neutral. Together, they form the central core of our atomic city. But what role does the nucleus play, you might ask? Well, think of it as the city's central business district, bustling with energy and activity. It's the powerhouse of our atomic city, holding everything together. The positive charge of the nucleus creates a strong attraction for the negatively charged electrons, which are constantly whirling around it. This force of attraction is so strong, in fact, that it keeps these buzzing electrons from simply flying off into space. So you see, the nucleus, small as it is, has a mighty role to play. It's the glue that holds the atom, and thus everything in our universe, together. Without the nucleus, our atomic city would descend into chaos, its electrons drifting aimlessly like lost commuters. So the next time you marvel at the complexity of the universe, remember the humble nucleus, quietly doing its job at the heart of every atom. Now, picture an atom as a miniature solar system. In this tiny universe, we have three main characters: protons, neutrons, and electrons. Imagine protons and neutrons as the sun at the center of this system, together forming the atomic nucleus. Protons carry a positive charge, and neutrons, well, they're neutral, no charge at all. Now, picture electrons as planets, whizzing around this central sun in orbits. These elusive particles carry a negative charge, and their paths around the nucleus are what we call energy levels, or shells. Let's paint a clearer picture. Imagine you're standing in the heart of a bustling city. The city center, filled with important buildings and offices, represents the nucleus, where protons and neutrons reside. The surrounding neighborhoods, filled with houses, parks, and shops, represent the energy levels where electrons live. Each energy level can accommodate a certain number of electrons. The first energy level, or the downtown area, can hold up to 2 electrons. As we move further out to the suburbs and beyond, these energy levels can hold more and more electrons. Electrons travel in these energy levels at breathtaking speeds, and their movement is more of a cloud-like blur than a perfect orbit. They're like city dwellers, constantly on the move, commuting back and forth between the city center and the outskirts. But what keeps these electrons from flying off into the ether, you might ask? Well, that's down to the attraction between the positively charged protons and the negatively charged electrons. It's a bit like how people gravitate towards the city center for work and then retreat to the comfort of their homes in the suburbs. Understanding these microscopic dynamics is key to grasping why elements behave the way they do and how they interact with each other. It's the fundamental basis of chemistry, and it all starts with the humble atom. So in essence, an atom is a bustling city of particles, each with its own role to play. Surrounding the nucleus is a cloud of electrons. These electrons are the lifeblood of an atom, giving it its unique personality. They move in energy levels or shells around the nucleus, like planets orbiting a sun. But these aren't perfect orbits. Instead, picture a cloud of buzzing bees, each bee representing an electron. This cloud is densest where the probability of finding an electron is highest and thinnest where it's lowest. Now here's where things get interesting. The arrangement of these electrons, especially those in the outermost shell, is what determines an atom's chemical properties. You see, atoms are social beings. They love to interact with other atoms, and it's these outermost electrons, also known as valence electrons, that are chiefly responsible for these interactions. For instance, imagine a party. The atoms are the guests, and the electrons are the topics of conversation. Some guests, or atoms, have more interesting topics, or electrons, to share, and hence interact more with others. Similarly, atoms with more valence electrons tend to be more chemically active. It's the electron cloud that defines how an atom will behave, whether it will be a wallflower or the life of the party, so to speak. In the atomic world, it's not just about the size of the nucleus or the number of protons and neutrons. It's the electron cloud that gives the atom its unique personality. So, in essence, the electron cloud is the social footprint of an atom in the universe. Imagine if you had a map that could guide you through the world of atoms. Well, in a way we do. It's called the periodic table of elements. This incredibly useful table is like a treasure map of all known elements, meticulously organized based on their atomic structure. Let's break it down. The periodic table is divided into rows and columns, known as periods and groups respectively. The elements are arranged from left to right and top to bottom in order of increasing atomic number. This means that as you move across each period from left to right, the atomic number of the elements increases by 1. Now the columns, or groups, are where things get particularly interesting. Elements in the same group have the same number of electrons in their outer shell, also known as their valence electrons. And it's these valence electrons that largely determine an element's chemical properties. So, elements in the same group tend to behave in a similar way because they share the same number of electrons in their outer shell. But that's not all. The periodic table is also divided into blocks. The S block, P block, D block, and F block, to be precise. These blocks represent the different regions in an atom where the electrons reside. The S block and P block elements are the main group elements. The D block consists of the transition metals, and the F block houses the inner transition metals. So you see, the periodic table isn't just a random collection of elements. It's a beautifully designed tool that helps us understand the properties of the elements, how they interact with each other, and even predict the properties of new, yet-to-be-discovered elements. It's fascinating, isn't it? All this information, neatly arranged into a table. It's like having the secrets of the universe at your fingertips. But remember, every table, every map, has its complexities, its little quirks that make it unique. The periodic table is no exception. The periodic table, in reality, is a meticulously organized map of the atomic world. Stepping from the introduction, let's dive into the two main coordinates of the periodic table, periods and groups. Picture the periodic table as a giant grid. Running horizontally across this grid from left to right, we have the periods. Each period represents a new energy level being filled with electrons. As you move across a period, each element has one more proton and is less metallic than the element before it. Now, running vertically from top to bottom, we have the groups. Elements within the same group or column usually have similar properties because they have the same number of valence electrons. This is quite handy, as an element's chemical properties can often be predicted just by knowing which group it belongs to. For example, Group 1 elements, also known as alkali metals, are highly reactive metals. On the other end, Group 18 elements, or noble gases, are known for their low reactivity. So you see, once you understand how the periodic table is organized into periods and groups, you have a key to decipher the behavior of elements. Periods and groups form the grid of the periodic table, a grid that not only categorizes elements but also hints at their properties. Now let's delve deeper into the secrets of the periodic table. The periodic table is divided into 4 distinct blocks: the S block, P block, D block, and F block. These blocks aren't mere categories, they represent the atomic orbitals that are occupied by electrons. The S block encompasses the first 2 groups of the periodic table, including the alkali metals and alkaline earth metals. These elements have their outermost electrons in the s orbital. Next, we have the P block, which includes groups 13 to 18. Here, the outermost electrons are in the p orbital. Yes, this is where you find the noble gases, those elements known for their reluctance to react. Then we have the D block, commonly known as the transition metals. Occupying groups 3 to 12, these elements have their last electron entering the d orbital. Last, but certainly not least, we have the F block, also known as the inner transition metals. These include the lanthanides and actinides, elements that have their final electron in the f orbital. But the periodic table isn't just about blocks and orbitals, it also reveals trends, patterns in atomic behavior across elements. One of these is atomic size. As you move from top to bottom in a group, atomic size increases due to the addition of energy levels. Then there's electronegativity, which measures an atom's ability to attract electrons in a chemical bond. Electronegativity generally increases as you move from left to right across a period and decreases as you move down a group. Lastly, we have ionization energy, the energy required to remove an electron from an atom. This tends to increase as you move from left to right across a period and decrease as you move down a group. So you see, the periodic table isn't just a chart, it's a story of atomic behavior. By understanding these trends, we can predict how different elements will react with each other, which is fundamental to the study of chemistry. The periodic table isn't just a chart, it's a story of atomic behavior. Let's shift our focus for a bit and look at the periodic table from a different perspective. Yes, you got it right. We are going to talk about the atomic orbitals. These orbitals are the regions around the nucleus where the electrons reside. The periodic table is divided into 4 blocks: the S block, P block, D block, and F block, each representing a different type of atomic orbital. The S block on the far left of the table comprises 2 groups, the alkali metals and the alkaline earth metals. The elements in this block have their outermost electrons in the S orbital, which can hold a maximum of 2 electrons. Moving on to the P block, this block includes groups 13 to 18 and houses elements with their outermost electrons in the P orbital. The P orbital can hold up to 6 electrons, which makes it significantly larger than the S orbital. Next up is the D block, also known as the transition metals. These elements have their last electron entering the D orbital, which can accommodate up to 10 electrons. Lastly, we have the F block. The F block, or the inner transition metals, includes the lanthanides and actinides. These elements have their final electron in the F orbital that can hold up to 14 electrons. So, you see, the blocks of the periodic table are not random groupings, but careful categorizations based on the electron configurations of the elements. By understanding the blocks, we can predict the electron configuration of an element and its chemical behavior. This helps in visualizing the atomic structure and expands our understanding of the elements and their characteristics. So the next time you look at the periodic table, remember, each block tells a different story about the atom's electron cloud. The world of atoms and elements is truly fascinating, isn't it? We've journeyed from the minuscule atom, the building block of everything, to the grand periodic table, a map of all known elements. Let's take a moment to recap. We began by exploring the atom, a tiny entity composed of even tinier particles, protons, neutrons, and electrons. We learned that the protons and neutrons reside in the nucleus at the center of the atom, while the electrons orbit in the electron cloud. These particles give each atom its unique properties, like its mass and charge. Next, we ventured into the periodic table. This masterpiece of scientific organization groups elements based on their atomic structure and properties. From hydrogen, the lightest element with a single proton, to heavyweights like uranium with 92, the periodic table houses them all. Remember how we talked about groups and periods? Groups, the vertical columns, contain elements that share similar characteristics. On the other hand, periods, the horizontal rows, show how these properties change across a single period. And let's not forget the transition metals, those elements that bridge the gap between groups, and the noble gases, the elements that are so stable they rarely react with anything else. Understanding atomic structure and the periodic table isn't just for the sake of knowledge. These concepts are the foundation of chemistry, physics, and even biology. They help us comprehend how materials interact, how energy is produced, and how life itself functions on a molecular level. So, as we wrap up this topic, remember that the world around us, from the air we breathe, to the ground we walk on, to the stars we see in the night sky, is made up of atoms and elements. Every moment, countless chemical reactions are taking place, driven by the properties of these atoms and elements. Remember, in every speck of dust, in every drop of water, and in every breath of air, there are countless stories of atoms and elements waiting to be discovered. Understanding the atomic structure is not just about appreciating the beauty of the microscopic world. It has a profound impact on many fields of science and technology. Every invention, every breakthrough, every leap forward in our understanding of the universe, it all starts with the atom. Consider the field of medicine. The design of new drugs and the development of innovative therapies often rely on our understanding of atomic interactions. By knowing how atoms combine to form molecules, we can predict how these molecules will interact with our bodies, leading to better treatments and cures. In materials science, the properties of atoms dictate the characteristics of the materials we use every day. The strength of steel, the conductivity of copper, the flexibility of rubber, all these properties are determined by the arrangement and behavior of atoms. And let's not forget about energy production. From burning coal to nuclear fusion, every energy production process is fundamentally about manipulating atomic structure to release energy. Looking forward, the future of science lies in our understanding of the atom. Quantum computing, nanotechnology, even the search for life on other planets, all these exciting frontiers of knowledge are rooted in atomic structure. So, as we delve deeper into the world of atoms and elements, remember this: every atom has a story to tell, and we're just beginning to listen. Our journey into the atomic world has just begun, and who knows what secrets we'll uncover next. The power of atoms is immense, and it's up to us to harness it. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.